Welcome back. This is the last and final video in the colligative property series, and we'll be wrapping it with osmotic pressure. What is osmotic pressure? I showed you this picture earlier in. I'm still not going to give you all the explanation. I think you can go and figure it out after I give you the preliminary explanation. Say you have a vessel and you have a permeable membrane through which things can go back and forth. Say this side is concentrated or highly concentrated solution, and this side is low concentrated solution. Okay. When you have the situation, I mean, they both contain solvent and solute. That's what makes it a solution, right? This is highly concentrated solution. This is low concentrated solution. This is comparatively highly concentrated because it has more solute versus this. And when a situation like this happens, the water goes from here, from the low side to the higher side, and to kind of dilute the solute molecule so that an equilibrium is established between these two sides. When an equilibrium is established, or the pressure that's generated in the process is called osmotic pressure. Now, this is a healthy cell, a red blood cell, which is isotonic condition, means that equilibrium is achieved. Now, I want you to tell me why this cell is almost like it's got nothing in it. It's almost shrunk so much. And what do these water means? What causes the cell to behave this way, which is a hypertonic situation? And this cell is it swells so much that it actually ruptured, and you can see it just coming out. And what's the meaning of this arrow going this way? What was the condition of whether it was the cell concentrated more or was it less concentrated? Just use this explanation and see if you can come up with some sort of explanation. And as with other components, osmotic pressure also an equation that you do not have to remember. Pi is the osmotic pressure, or is gas constant. Again, why are we using this? Is there volume? Yes. C is molarity, right? Which is moles over liter. Because volume is involved, we're using this gas constant. I is Van 't Hoff factor, and T must be in Kelvin. Keep in mind, the boiling point and freezing point were molality. Osmotic pressure is molarity. Okay, so let's do a sample problem. Determine the osmotic pressure of a solution containing 10 grams of glucose dissolved in 5 liters of solution at 23.5 degrees Celsius, right? So what are the things we know? Well, glucose is a non-metal containing compound, so the entire compound I value is 1. And we know R value is 0.0821. We know temperature is 23.5 degrees Celsius, which equates to 273 plus 23.5, which is 296.5 Kelvin. So if we can find a molarity, which is C, then we can solve for osmotic pressure, which is moles over liter, right? Well, glucose is 12 times 6 plus 16 times 6 plus 12 is 180. So glucose molar mass is 180 grams over 1 mole. And we're starting with 10 grams of it. So 10 grams over 180 grams over 1 mole will be 10 over 180. It's 0.055 moles. And we are dissolving that in 5 liters. So divide that by 5 liters will give us our molarity. It's 0.011 molarity. Let's put it all together. So pi equals 0.011 times R is 0.0821 times T is 296.5 times I is 1 because it's a non-metal containing compound. So that times 0.0821 times 296.5 is 0.270 atm. That's the osmotic pressure, and that's the end of the concept. It's very easy. So I have said everything I have to say about this concept, and this is the practice problem I want you to do. This is tricky, but I'm guessing you can do this. You have to figure out the molar mass of the protein. Give it a shot, do it as part of your My Thoughts, and of course at some point I will intervene and help you understand this problem. But you still have to get through most of what I said earlier. Let's see if you can determine the molar mass of the protein, and that concludes colligative properties.